In the A-level physics required practical for Boyle's law, you're likely to have a setup a bit like this, where you've got a syringe that's got a mass of air in it, you've got string, we've got some masses, and we've got a clamp to hold it up with. So we're going to talk about what Boyle's law is expected to prove, and also how we expect it to do it. The method for this itself isn't too tricky, but actually what you've got to calculate and how you plot your graph can be a little bit difficult. So Boyle's law, if we didn't know, states that pressure is inversely proportional to volume of a gas. This requires it to be at constant temperature. So with a setup like this, how can we go about doing this? So experimental method, let's have a look. The first step is to measure the inside diameter of the plunger before you set the whole thing up. You're going to do that using a vernier caliper. We'll talk about why you do this later, but it's so you can calculate the area, so we can calculate the pressure. So we're going to calculate the cross-sectional area using pi d squared over 4 or pi r squared to calculate a cross-sectional area, which we just need to do one time because it's a constant value. Next, what we're going to do is take the syringe again. We're going to draw in about 4 milliliters of air into the syringe. When we've done that, it's really important we make it a fixed mass or fixed number of moles of gas. So we're going to have to make sure we fix the other end of the syringe by clamping and rubber tubing over the end to make sure that it is nice and secure and that no gas can leak in or out. The next thing we do is attach the mass hanger via some string to the other end of the syringe, the plunger end, and then we're The next thing we're going to do is attach the mass hanger via some string to the other end of the syringe, the bit with the plunger in, and then we're going to basically hang it there, let it get settled, make sure it's not moving too much up and down so that it's not stuck, and then we're going to start adding our masses. So we're going to add initially with just the mass hanger on it, we're going to record the volume, then we're going to add masses one at a time and record the volume on the syringe. You're going to want at least 8 results to get a graph, and you're going to want to repeat readings as well. So those are the two things we're measuring. We're going to change the mass, record that, and then we're going to measure the volume. However, that is not by far the end of the story. When you're doing a table of results for this practical, you want to make sure you've got a lot of column headings because we've got a little bit of calculations to do. So we're going to vary the mass. We're going to record the volume. I haven't put the units in this table just to save room. Then we're going to record 1 divided by the volume because we're going to plot that on our graph. Now, to find the pressure, we're going to need to do the force divided by area. Force divided by area, in this case the force is weight, so it's mg, the mass we've measured in kilograms, times by 9.81, divided by the cross-sectional area in meters that we calculated earlier. However, that's only the pressure we're applying, that's not the actual pressure of the gas. As we apply pressure downwards on the syringe, we're actually decreasing the pressure in the gas. Without a mass hanger there, it's just that atmospheric pressure, which is 101 kilopascals or 101,000 pascals. So therefore, to find the overall pressure of the gas, we have to do the atmospheric pressure minus the applied pressure, so minus mg over A. So you're going to need a column in your table for that as well. So the purpose of this practical is to prove that pressure is inversely proportional to volume. So we could plot a graph of pressure and volume and look for an inverse proportionality curve. However, that's going to be a bit fiddly, and also curves can look in different ways. So we're going to have to plot instead a graph of pressure versus 1 over volume and see if it's a straight line through the origin. So on our graph, we should have pressure of the gas, which is our final column, in kilopascals, and we should have 1 over volume, which will be in milliliters to the minus 1. Well, it doesn't matter too much about the units here because we're only looking at the relationship. So we should find that these two things are directly proportional, which shows that the Boyle's law is correct, which is great. And if you wanted to calculate the gradient, that would equal at any point pressure over 1 over volume, which is PV, and that should be constant throughout. There are some common errors in this practical we need to be aware of. So as we mentioned earlier, we need to ensure the gas is at constant temperature to ensure that this relationship works. This only works at constant temperature. So we need to make sure when we apply pressure to the gas, we leave it for a few seconds after adding masses so that it sort of maintains a constant pressure with its surroundings. We also need to try and ensure that the syringe doesn't sort of stick to its holdings. Now, how we do that is we give it a little wiggle, like we mentioned earlier, to make sure it's free to move. If that doesn't work, you can lubricate it to make sure it's free to move. Otherwise, there's no point doing the whole practical because you're going to have it go up by lesser or smaller amounts than it should do. Last thing is to read the volume at eye level to make sure you avoid parallax error, and try and use a syringe with a low enough resolution so that it's not just sort of 2 milliliters at a time. So the safety of this practical, we're obviously using masses, so we want to make sure we do it in the center of the table to avoid masses falling on people's feet, and it's a really good idea to have a clamp or a counterweight on the clamp stand itself to ensure it doesn't topple over when you're adding masses to it. This experiment is a good chance to practice some uncertainty analysis. So uncertainties in this practical, you're not going to be asked, because there's nothing to calculate with a gradient, there's no uncertainties with lines of best fit or things like that, unless there might be an exam question where you're asked to work something out, but I can't think necessarily what that would be. So uncertainties here are limited to just the uncertainties in the pressure and in the volume. So when we worked out the pressure, this is the pressure applied, we said it is equal to the mg, the weight divided by the cross-sectional area. To calculate the cross-sectional area, we used a vernier caliper. So we should be able to work out the percentage uncertainty in the cross-sectional area by using the percentage uncertainty in the diameter. So the general rule is here, because cross-sectional area is equal to pi d squared over 4, is that the cross-sectional area in the area is going to be twice whatever it is in the diameter. That's because you've got the factor of d squared. You're using d twice. You're kind of compounding the error, so to speak. So if we were to do an example of this, in the diameter, we've got a measurement, for example, of 2.1 centimeters, which, as I'm writing this, it should be an extra decimal place because vernier calipers measure to 0.1 millimeters. Let's just go with this for now. So in this example, you'd say 0.1 divided by 2.1, the reading, which equals 4.8%. So therefore, the percentage uncertainty in the area would be double that, so that would be 9.6%. What about the volume? So the volume, there's no calculations to make. However, we are reading off the side of a syringe, and obviously the syringe has a resolution. So in terms of the actual piece of apparatus itself, let's say, for example, we had a reading of 4.2 milliliters, which if we started at 4 is not unreasonable. That would be plus or minus, let's say 0.2 milliliters. You'll have to check your syringe for this one. Some of them go up in sort of 1 milliliter, some of them go in 2 milliliters, some go up in 0.1s, 0.2s. It just depends, really. So in this case, as an example, we'd say the percentage uncertainty in the volume is equal to the resolution, so 0.2, or the uncertainty 0.2 divided by the value 4.2, which again gives us a percentage uncertainty of 4.8%. Now, what about 1 over volume? Because that's what we plotted on our graph. Well, actually, it will be the same. The percentage uncertainty in 1 over the volume will be exactly the same as the percentage uncertainty in the volume itself. That's because you're just using the volume once. Doesn't matter what you're doing to the number. You've not got any other variables or factors in there. It's not squared or anything like that. So we just include it once. This one last thing with the pressure is that because it's the atmospheric pressure minus the applied pressure, we don't have any uncertainty values given with the atmospheric pressure. So we just need to ignore that for now when you put that in your graph. So there we go, that's the Boyle's Law Practical. Charles' Law Practical is in a separate video, that's part of the A-Level Required Practical as well. And let me know if you've got any questions in the comments below. And thanks for watching.